Hi everybody, welcome to another video in differential equations, section 8.3. This is the most important section in the chapter where we use a power series to write a solution to a linear differential equation. The tool we need is to combine power series. We need to know how to combine series in order to write the solution. Right. In order to combine power series, we will need to have the series that start at the same index. So for this problem, we don't have it start at the same index, n equal to 0, n equal to 2. First, we have to make sure the index start at the same number. And then the second we need to check is that the power have to be of the same degree. Right, so two things. Same degree on the x and the same index, it start at the same index. Alright, there will be two solutions to this. The first one is that I prefer this way, which is first, since we need to have the index to be the same, so why don't we let them equal to k? So we let this equal to x of k, and we'll need this to x of k as well. So the power in both series will be have the x to the k power. Right. Now, if we do that on the first series, we'll have k equal to n minus 2, and on the second series we have k equal to n plus 1. Right, so that's on the first series, second series. Now, if k equal to n minus 2 plus 2 on both sides, n equal to k plus 2 for the first series, and n equal to k minus 1 on the second series. Now we substitute k plus 2 in here. Pretty much in everywhere we see n. So n, k plus 2 in for n, k plus 2 in here, k plus 2 minus 1 is k plus 1, k plus 2 into n, and k plus 2 minus 2 is k. Right, so we substitute k plus 2 in all of this n. Next, we substitute k minus 1 into this n, and this n. So we have k minus 1 equal to 0, c of k minus 1, and x of k, because n is k plus 1, n is k minus 1, k minus 1 plus 1 is k. Now both of them have the k power, which is good. We take care of one of them, we took care of the power. Now what we do next is we make sure that they start at the same index. Now this one starts at 1, this one starts at 0, which means if we want them to start the same one, we have to split one term out from the first series. Right. Note that the first series start k equal to 0, second series start 1. In order to add them, both must start the same number. So we split one term from the top. So this one starts 0, right? Now if we split one term, so this is going to be at k equal to 0. When k equal to 0, put 0 in here, we have 2 times 1, right? 0, 0, c of 0 plus 2, x of 0. So we have 2 times 1 times c of 0, x of 0. X of 0 is 1. So we have 2 c naught. Sorry, wait. k plus 2, so this will be 2. Sorry. So we have 2 c2, x naught is x to 0 power is 1, so that's what we have. And once we split our one term, we can start the summation from 1. And now both of them start at 1. We can combine them, factor out x to the k, and we just combine the series. So that's one way to do that. Take care of the power first, and then take care of the index. Now the next or we can do this the other way around. Take care of the index first, and then we'll take care of the power. Right, now, first, we check the index, where it start. This one start 2. If you put 2 in here, this series start x to the 0 power. If you put the lower limit here, this series start 1. Because of that, in order to add them, this one start at x naught. I should write this. Start at x to the 0 power. This series start at x1, x to the first power. Once again, if we want them to match, we split one of them, one term out of it. So we're going to put 2 in here. So we have n equal to 2. We will have 2 minus 1, c of 2, x of 2 minus 2. Yeah, put 2 in for n here. And that 2 times 1 is 2, c2, x to 0 power is 1. Now we split our one term for n equal to 2. The series, the summation now start from 3, n equal to 3 to infinity. Now do that, we will take care of the index, the lower limit. So it start the same number. Now, next we're going to match both of them equal to k. Now we do this the same way as we did before. This equal to x to k, and this equal to x to the k. So we have k equal to n minus 2 and n equal to k plus 2. This will be the same as the other. And then we substitute k plus 2 in for this n, and substitute k minus 1 in for this n, and we have the series and then combine. Right, so pretty much there's two things. Make sure the power have the same, the power of x have the same degree when we combine them, and both of them start at the same index, so we can combine the series. If they are not even, then we have to split our few terms to make them balance before we combine. Right, and finally, one more step, one more thing that we can check. Look at this one. Okay. Sorry. Right. So this is the original prompt, and this is the answer. So when we combine, of course, just ignore that term for a moment. That's usually easy to check. Now we just need to check the summation itself. Note that in here we have the power of x is n minus 2. This index is c of n, therefore the coefficient here is 2 more than that. And we have 2 more than that and 1 more than that. Right? So if this is k, this will be k plus 2, this will be k plus 2, this will be k plus 1. So yeah, so bottom line is the power of x here will be 2 less than this and 1 less than that coefficient, and we can check the power of k will be 2 less than that and 1 less than this coefficient. And then the next one, the power will be 1 more than the coefficient, the index of the coefficient. The power is 1 more than the index of the coefficient. So that check. Right. So we need to know how to do this first before we can write the solution to a differential equation. Right. Now combine this. There are two ways to do this, and I prefer to go with the first one. Just take care of the index. Just take care of the power first, because I did both of them, and this kind of solution I could think that is less room for error. I mean, I did both of them, and the first type of solution produced with less error. Right, so match coefficient. So first, this have to be x to the k, right? And this have to be x to the k as well. So for that, in this series we say k equal to n minus 1. If that is the case, n is equal to what? Plus 1 on both sides, k plus 1. So for the first series, that's what we use. On the second series, k equal to n plus 2. So subtract 2 on both sides, n equal to k minus 2. So the first series we're going to use this, the second series we're going to use that. Now substitute back into our problem. Right, n here, which is k plus 1. Equal to 1. By the way, doesn't matter when we substitute infinity, still infinity. So that's why we don't have to concern much about that. If this is not infinity, then we have to change that as well. Right, n, right, k plus 1. And then c of n, well, n is k plus 1. X of n minus 1, well, n minus 1 is k. By the way, when we do this, we should have x to the k. Right, now plus 3 summation. Next, on this one, we let n equal to k minus 2. C of n k minus 2, and then x to the n plus 2. Every time we have n, I'll use substitution, and by the way, n plus 2, so that should be k. By the way, when we do this substitution, all of them should be x to the k. Right, now just take care of the lower limit. Subtract 1 on both sides, we have k equal to 0. Just copy everything else. So move the 2 over, or add 2 on both sides, k equal to 2. C of k minus 2, x to the k. Right, now both of them have x to the k. We should be able to combine them if the index start at the same number, which is not. Now this one starts 2, this one starts 0, meaning that we have to turn this into a bigger number. We cannot turn this to a lower number. So we go from 0, so we take care when k equal to 0 first, and then when k equal to 1. After that, we can have k equal to 2. Now, when k equal to 0, now if you put 0 in for k, what do we have? 0 plus 1. I put 0 in for k. C of 0 plus 1. X to the 0. Now that term is when x equal to 0. I mean where k is equal to 0. And then we add when k equal to 1 into the summation. K equal to 1. Once we write those two terms, the series now will start at 2. We took care when k equal to 0, k equal to 1. Now k can go to 2 to infinity. The rest will stay the same. Now let's simplify this. By the way, we can say that series equal to, all of them are equal. Right, 0 plus 1 is 1. C of 0 plus 1, so C1. X naught is 0. And x to 0 power is 1. And then we have 2. C of 2. X to the first, which is x. Now we can combine the power series. Both start from 2 to infinity. And then we have k plus 1. C of k plus 1. I can factor out x of k because both of them have it. Right. Simple enough. And just like the previous one, we can check that the power is 1 less than the coefficient. Right, this is k, 1 less than the coefficient. 1 less than the index, sorry. So the power is 1 less than the subscript or the index. And the power is 1 less than the coefficient. So yeah. So this is the power 1 less than the index, 1 less than the coefficient. Next. See. Have to be very careful. This one usually there's a 3 here, right? I forgot. And you can multiply here the 3 inside instead. So then we have 3. So now we check. The coefficient should have 3. The power is 2 more than the subscript. The power is 2 more than the subscript. So that check. Yeah. So it's good to go back and check. So when I go back and check, I forgot the 3. So there it is. Right. Like I said, I prefer to do it this way, where we check the power of k first, and then we will know how many we split. By the way, don't forget the tiny detail of the 3 the coefficient. Right. Let's look at another example. Combine the power series. Okay, that's what we have. Right. First, of course, we'll take care of this. Turn that into x to a k. To do that, we will let k equal to n minus 1. And with that, n is equal to k plus 1. Now, we turn this to x to the k as well. So k is equal to n plus 1. So n is equal to k minus 1. Right. Now substitute into a problem. Just put in this into parentheses. So we know that part is not equal to what we're about to write. Right. Just copy everything. Whenever we see n, we replace by k plus 1. And k plus 1. C of k, C of n, which is k plus 1. X to the n minus 1. By the way, we need x to the k there, so there. Right, minus 5. We have n here. This time n is equal to k minus 1. Equal to 0. C of n, which is k minus 1. X to the n plus 1, which is xk, and that's exactly what we need. Right, let's simplify this. K plus 1 equal to 1, subtract 1 on both sides, k equal to 0. And then the series will stay the same. Plus 1 on both sides. Right. Next, this one start 0, this one start 1. We need to match the lower limits. So we have to split out the case when k equal to 0. Put 0 in here. Yeah, put 0 for k. And when we do that, the series now can start from 1. I will multiply the 5 inside. Now that gives us C. That's 1, C, 1. X to the 0 power is 1. So that's C1. And then the summation. Both of them start from 1 to infinity. And the power of xk, so I can factor out x to the k power. So I have k plus 1. C of k plus 1. Subtract 5. C of k minus 1. All of which times x to the k. And final check. The power is the same as the coefficient. Sorry, I didn't look at that. Okay. The power is n minus 1 and the coefficient is n, so the coefficient is 1 more than that. Yes. And the subscript or the index is 1 more than the power. Yes. The power here is 1 more than the subscript. K is 1 more than k minus 1, and then it's minus 5. Yeah. So yes, that's what we have. Right. So those are very important skill in order to write a power series solution to a differential equation. Right. Now, just go over the theorem first. Upon x naught is called an ordinary point of the equation if both p of x and q of x are analytic, meaning that we can write as a power series representation. If it is not an ordinary point, we call that a singular point. Now we only focus on write the solution on the ordinary point. And the singular point, that will be in the next section. Right. Once again, ordinary point where we can write a power series representation for p of x and k of x. Right. By the way, in class I will do some a relatively simple example. When you go to the final assembly view, they are a little more complicated problem, and there's a solution, the video solution for those final assembly view as well. But when you see the review or you do the homework, you will see that there will be the problem will be a little bit different, but the way we do that will be the same. Right, now the point here is of course we are trying to write the solution to a differential equation, because that's the main purpose here, right? The center at the ordinary point, the simplicity x equal to 0, right? Now first, because it is a power series solution, so we can write y is equal to that, right? Power series h of n times x to the n power, n go from 0 to 1. Now if we take derivative, the index, when we take the derivative, the index will increase by 1. We talked about this in the previous section. When we differentiate, and then we differentiate term by term, the power n goes down and the original power n minus 1. Now we substitute into the original equation derivative, that the function that time to x. Now when we multiply the 2x into this, if we can multiply the 2x inside, x times x to the n give us x to the n plus 1, right? That's why we multiply an x inside. That's what we have. The reason we can move the x inside because the index is n. If we have n something, we cannot bring it inside, but we have something else other than n. So yeah, so we move that inside. Right. Now, the next problem is just combine these two series, because we did that the similar way earlier. So I will use the method that is in the solution number 1, meaning that we will match the coefficient first, x to the k, and we'll match this x to the k. So on the first series we have k equal to n minus 1, or n is equal to k plus 1. The second series, n plus 1 is k, so n is equal to k minus 1. And then we substitute in k plus 1, substitute into n. This is n, this is n, this is n, and the power of course to the k. Right, we substitute all of that, and then we substitute k minus 1 into n, right? N, k minus 1, and this should be x to the k. Right. When we simplify, this is equal to 0, and then we have that. Now, this start from 0, this start from 1. We have to split one term out. Right. Let's use pencil. When k equal to 0, we have 0 plus 1, 0 plus 1, a of 0 plus 1, x of 0. Yeah. So this is 1, a sub 1, x to the 0 is 1. So we just have a1. So this is when k equal to 0. When we take care of that, the series now start from 1 to infinity. Right. Now we can combine them. Factor out x to the k, and we have that. Now, the nice thing about this, the fundamental of the power series solution, is that the right hand side is equal to 0. On the left we have a polynomial representation. Now, the polynomial equal to 0 when all the coefficient equal to 0, right? All the coefficient equal to 0. That means the a1 here has to be equal to 0. Yep. And then we have this must be equal to 0. Every coefficient has to be equal to 0. So we let that equal to 0. If we solve for k, a sub k plus 1 here, so move the negative 2 to the other side and divide by k plus 1, and we have this coefficient, that relation. Right, in terms of coefficient, what do we have? We have the first a1 is equal to 0, right? If we want a2, if we start with if we want a2, we're going to put 1 in here to get a2, right? So k equal to 1, we have a2 is negative a naught. If we want a3, we're going to put 2 in for k. That's what we have. And if we want a4, k equal to 3, and we have this. And then a6 and a5. Right, we can see that on the even terms, on the k even, it's going to be 0. Right, now with that, we have a naught, which we don't know. a1 times x plus a2 x squared, a3 x cubed, and so on. A naught we don't know, which is fine. A1 is equal to 0. A2 negative a naught. A3 is 0, and then so on. So when we put all the coefficient in, that's what we have. So essentially, we just combine the power series. If it is equal to 0, all the coefficients have to be 0, and then we just solve for that recursion relation, and we have all the solution. So that's all we do. So simple enough, right? Now let's look at the second order differential equation. Right. So first, well, it didn't say anything, but one thing we have to write is that write the first non-zero term for the series solution centered at an ordinary point x equal to 0, if we want to be precise about it. So write the first with assuming write the first 3 non-zero terms for each constant, assuming that x equal to 0 is an ordinary point with x equal to 0 is an ordinary point. By the way, if this series is not start at x equal to 0, it will be something, but if it starts some other numbers, then we have to write this instead of just x. But we assume that at x equal to 0. So to keep things simple, we just assume that the power series will be at x at the center at 0. So in that which case we can say let the function be the power series solution k. Right. Let's go with n, because later on when we change the index, we're going to introduce k later. So let's start with n equal to 0 to infinity a sub n x to the n. Alright, now we take derivative. Every time we take derivative, the index will increase by 1. except later on that will be different, but in this case index, and then derivative of x to the n, we take down the n, a sub n is still the same because that's constant. X, the power will reduce by 1. Right, so that's just the derivative, but notice the index that we increase by 1. Now second derivative, once again the derivative we have to increase the index by 1. So we have n, and derivative of this, take down n minus 1, a sub n x, and the power decreased by 1. Right, so we have the second derivative, we have the first derivative and the function. Now substitute back into the function, the original equation, I mean. So second derivative will be that. And then plus x squared multiplied by the function. The first thing I'll do is multiply this inside, so that makes this power n plus 2. Right, now we change the index. I mean change so that both of them equal x to the k. Right, so we need this to x to the k, and this x to the k. Right, so k equal to n minus 2. Of course, if that is the case, plus 2 on both sides, n is equal to k plus 2. On this series, k is equal to n plus 2. So n is equal to k minus 2. Right. Now, since this one has the equal sign, I don't want to write equal to, because I'm going to write both sides of the equation. Right, now first, the series. I have n here, that should be k plus 2. So every time we have n for that series, use k plus 2. N k plus 2. N minus 1, k plus 2, minus 1. A sub n, there's n, k plus 2. X to the n minus 2, n minus 2 is k. By the way, like I said, both series should have x to the k. That's the first series. Second series, I will have, instead of n, it will be k minus 2. And then infinity. A sub n, k minus 2. X to the n plus 2, n plus 2 is k. Equal to 0. Right. Now let's simplify this a little. K plus 2 equal to 2. Subtract 2 on both sides. K plus 2, k plus 1, a sub k plus 2, x to the k. And then combine. K minus 2 is equal to 0, so k equal to 2. A sub k minus 2, x to the k. Right, so both of them have x to the k, which is good. That's why originally we use n, so we don't want to be redundant later on. We want to change the index anyway. Right, now, this start at 2. We have to write this, both of them have to start at 2. So we split out two terms. When k equal to 0, when k equal to 0, put 0 in here. 0 plus 2, 0 plus 1. A up 0 plus 2, x up 0. Right, and then next, k equal to 1, 1 plus 2, 1 plus 1, a up 1 plus 2, x to the first power. Right. When we write those two terms, the series now will start from k equal to 2. So if this k equal to 0, so plus 2, 0 plus 1, x to a to sub 0 plus 2, x to 0, k equal to 1, 1 plus 2, 1 plus 1, 1 plus 2, to 1. Yep. Now the series will stay the same. I just write it smaller because it looks like I don't have a lot of space left. Right, now let's simplify this. 2 and 1, so that's going to be 2. This is a2, right? Two, a2, x to 0 power is 1, so let's just have that. Now this 3 times 2 is 6. A3 x to the first, or just x. Now we write these two series, and we should just copy and paste. Now just factor out x to the k, combine the series. 2a2, 6a3, k plus 2, k plus 1, a sub k plus 2, factor out x to the k, plus a of k minus 2. Now, we have the series combined. All of that equal to 0. A polynomial equal to 0, which means every coefficient have to be, we have all the coefficients equal to 0. So the a2 have to be equal to 0. And the 6a3 have to be equal to 0. Right, all the coefficients equal to 0. And that coefficient have to be equal to 0. Right. Before I go further, I will need to check with the original series, meaning this one. Okay. Yeah. Pay attention to this one. And that. Right. Notice the power n minus 2, so the coefficient will be 2 more and 1 more. So powers k, 2 more and 1 more. Okay, good. The index n minus 2 and n, the subscript is n, the power is n minus 2, so the index have to be 2 more than the power of k, 2 more, which is good. And then plus. On the second series, the power is 2 more than the index, 2 more than the index, so which is good. Right. Now, next, 2a2 equal to 0, meaning that a2 is equal to 0, so we have one coefficient. 6a3 is 0, so a3 is equal to 0. Now for this one, we have to simplify. We have a of k plus 2 and a of k minus 2. If we solve for a of k plus 2, we solve for the bigger index. We move this to the other side, becomes negative, divided by k plus 1 times k plus 2. Right, so what we have, since we start from a2 and a3, we don't know. So in that case, what we should write is that a naught is don't know, or we just say is is a constant, or could be any constant. Right, let's say is arbitrary constant. A1 is also, because it is not, or just by default it's just a constant, is arbitrary constant. Right, it's just a constant. It is not mentioned in here, so we just say that is a constant. Right, now we have a naught, a1, a2, a3. Next we need a4. In order to have to a4, k must be equal to 2, right? So let's choose when k equal to 2. K equal to 2, put 2 in here. A of 4 equal to what? Negative. If we put 2 in here, 2 minus 2 is 0. Negative a naught over 0 plus 1. 0 plus 2. and that is 1 times 2 is 1/2, so we have negative 1/2. Sorry, k equal to 2, right? So put 2 in for k. Sorry, 2 in for k, and that 3 and 4 should not be negative 12 a naught. Right, so that's good. Next, k equal to 3. Put 3 in for k. A5 equal to negative 8. 3 minus 2 is 1. 3 plus 1. 3 plus 2. So I have negative A0, A1. 3 where 4 times 5 is 20. Right. Next, we need A6. So k equal to 4 here. K equal to 4, so 4 minus 2, so negative. A2, 4 plus 1, 4 plus 2. A2 is equal to 0, so this is equal to 0. K equal to 5. 5 plus 2 is 7. And we have negative 5 minus 2 is 3. K is 5 plus 1. 5 plus 2. Doesn't matter though. A3 is equal to 0. Right. So where do we start? Well, the problem did say write the first 3 non-zero term for each constant. Now that makes sense. For each constant, A0 and A1, we're going to need 3 of them. So we need 1 more. We have A0, that, and then 1 more. Right, k equal to 6. 8 of 8 equal to 6 minus 2, negative A4. 6 plus 1, 6 plus 2. Right. 6 plus 1 is 7 and 8. 1 over 56. Negative times A4. We have A4 is negative 1 over 12 A0. So what is 12 times 56? 672. A0. And then k equal to 7. A 7, so it will be 9 equal to negative 8, 7, so that's my negative A5, and then 7 plus 1, 7 plus 2. That is 8 times 9, 72. So 1, negative 1 over 72. A5 is negative 1 over 20. So 20 times 72, actually that is easy. 1440, 1440, A1. So can't run out of space, but that's what we have. And now finally, the solution. We have y equal to a naught. Now if I just write some series first and then I will spell out the terms. N equal to 0 to infinity a sub n x to the n. So a naught plus a1x a2x square a3x cubed and so on. So the series, what do we have? A naught, arbitrary constant, can do anything about that. A1 also a constant. A2 is equal to 0 and 0. So this, just going to say 0x squared for A3, 0x cubed. Now for x, next to the A4, A4 is negative 1 over 12 a naught x to the 4th. A5 negative 1 over 20 a1 x to the 5th, because that is A5. A6 7 8 and 9. X to the 9, and then that keep going. And finally we can write the solution. We can factor everything that have a naught. So we have a naught here, and everything with a1. The others are 0. Now put them together, we will have factor out a naught (1) minus 1 over 12 a naught factor out, and then we still have x to the 4th plus 1 over 6 7 2 a naught factor out, but we still have x to the 8, and this we keep going in terms of a1. There's x, factor out a1, and then we have minus 1 over 20, factor out a1, still x to the 5th, 1 over 1440, factor out a1, still x to the 9. So we have two, the first 3 non-zero constant for each coefficient. Right, now if you think about this, the solution, this is the second order differential equation. So we have C1y1 and C2y2, kind of the same thing, so that is a constant. Right, so that's what we have, that first example. Now let's look at another example. By the way, just make sure that on this one, when we do that, the solution should be at the bottom here. Right. Now, once again, write the first three non-zero terms for each constant, and assume that do the power series at x equal to 0, at the center equal to 0. If it's not at 0, we have to use this, and the calculation is a lot more complicated. Actually, we have an example like this in the next section. But once again, x equal to 0 is an ordinary point with meaning that we write the solution, we will write the solution x equal to 0, and there will be no problem with it. Right, so let y be the series a sub. Sorry, originally we use n, or we can use a sub n or c of n, it doesn't matter. X to the n, then take derivative. We can almost copy and paste from the other problem. Index will increase by 1, the power rule, and a sub n x to n minus 1, second derivative, n equal to 2, and n minus 1, a sub n x sub n minus 2. Right, substitute into the equation. We have second derivative, which is this. By the way, if it's just plus x is too simple, let's change that to something else. Right. I will change this on the note before I post this online. Let's say minus 2 minus 2x. If it's minus 2, it's too simple. Once again, I will change that before I post online, so on your note there will be no problem. So 2x, right, a little more interesting. Right, second derivative is going to be that. Minus 2x times the function. Right, first I multiply the x here inside. Actually multiply the 2 also. Multiply that inside. Especially the power. X times x to the n is x to the n plus 1. The 2 inside, a sub n, then x and x to n multiply the power will be x to the n plus 1. Right, now the index. This to x to the k this equals x to the k. So k equal to n minus 2 and n equal to k plus 2. The other we will have k equal to n plus 1, n equal to k minus 1. Right, so we change the index as those two. Right, summation. This one has a k, this one has an n. That will be k plus 2. There's an n, k plus 2. There's an n, k plus 2 minus 1. There's n, and the power must be extra k. Right. That's the whole point of we substitute changing from n to k. Next, there's an n here. This n is going to be k minus 1. We have 2 a's of n, n k minus 1. X and plus 1 is k. Or if we put k minus 1 here, k minus 1 plus 1 is k. Right. Now let's just simplify this a little bit. K equal to 0 to infinity, k plus 2, k plus 1, a of k plus 2, x of k, right, k minus 1 plus 1 on both sides, k equal to 1. Now this one start 1, this one is 0, so we have to split one term from this series. So both of them will start at 1. Right, when k equal to 0, put 0 for k. Yeah. So usually I recommend multiply the 2 in front, so you have that 2 inside the summation. Usually if there's something outside and you focus on the summation, you might forget the number in front. So if there's a number, multiply inside. So just like, don't make a mistake like I did earlier. K equal to 0, k equal to 0, 0. Zero plus 2. X 2 to 0. Right. Once I write that, the series now can start from 1. I simplify that to 1, so that is just 2a2. x to the 0 power is 1, so just do a2 pretty much. 2 times 1, 2, a2, right. Now combine the power series. K plus 2, k plus 1, a sub k plus 2, factor out x to the k minus 2, a of k minus 1. Right, let's pause and check. So we'll leave that. Right, this 2. And this. Right, the power, the coefficient will be 2 more. Okay, powers k, this is 2 more, n minus 1, 1 more, yep. N will be 2 more than the index, than the power, yes. So in relation, n and n minus 2, so will be 2 more than that, 1 more than that, 2 more than that, which is good. And then minus 2, actually we should look at this one. Then minus 2, a, the subscript is 1 less than the index, subscript is 1 less than the power, so a sub n, n plus 1, subscript is 1 less than the power, so that's good. We combine them, so that look good there. Next, the series equal to 0, meaning every coefficient has to be 0, meaning the a2 here to a2 has to be equal to 0, and then all of that, all of this coefficient has to be equal to 0. So k2 k plus 2, k plus 1, a sub k plus 2 minus 2, a of k minus 1 equal to 0. Right, now 2a2 equal to 0, so we have a2 is equal to 0, and then with this recursion, by the way, if we change the problem, the solution will be something else, so just ignore what we have at the bottom. I changed the question, forgot to change the answer, ignore that. Right, now if we solve for a sub k plus 2, if we focus on this, I take the 2k minus 1 to the other side, move that to the other side, it becomes positive. And then I have k plus 2, k plus 1. Now, we have a2 equal to 0. In this series, in this solution, there's nothing, a naught and a1 are not mentioned. So we can just say a naught and a1 are constant. So we have a naught, a1, a2, 0. Now we need to have a3. To get a3, k has to be equal to 1. So k equal to 1. We're going to put 1 in for k. Give us a3 equal to 2. K is equal to 1. So 1 minus 1 to a naught. K plus 2, k plus 1, k is equal to 1. 1 plus 2, 1 plus 1. So what do we have here? It's going to be 2, 3 and 2 with 6 at the bottom. 2 over 6 is 1 over 3. A naught. Right. Next. K equal to 2. We have 8 of 2 plus 2, 4. Will be 2. 2 minus 1, A1. 2 plus 2, 2 plus 1. So 2 over 4 times 3, so this is 1 over 6. One over 6 A1. See. Right. K equal to 3. K equal to 3. That gives us A5. K equal to 3. 3 minus 1. A2. 3 plus 2. And 3 plus 1. Remember, A2 is equal to 0, right? So that is 0. Keep going. K equal to 3, now K equal to 4. 4 plus 2 is 6. 2, A, 4 minus 1 is 3. K equal to 4. 4 plus 2, 4 plus 1. Right. Now, we have 2 over 6 times 5. So that is 1 over 15, right? Yep. 1 over 15. A3 is what? 1 over 3 A naught. Will be 1 over 45. Right, keep going. K equal to 6. K equal to 4, we have A6. K equal to 5, we have A7. Actually, I should write this. Take a lot more space. Now K equal to 5. 6. I'll put 5 in here. 7 equal to 2 times K equal to 5 to A4 over 5 plus 2, 5 plus 1. Right, so what we have is 2 over 5 plus 2 is 7. 5 plus 1 is 6. 2 over 42 or 1 over 21. A4 is 1 over 6. A1. Right, 6 times 21. Right, of course we can keep going, but we're going to stop here because once again we need the first three non-zero terms for each constant. We have a1, 2, and the constant by itself will be 3. Right. So the solution n equal to 0 to infinity h of n x to the n will be a naught plus a1x, a2x squared, a3x cubed, and so on. Then we can write a constant. A1 is also an arbitrary constant. A2 is 0. A3 is 1/3. A0, that is A3, right? So to the third power. A4, 1/6. A1 x to the 4. A5, that is 0. A6, 1/45. A0. A7, 1/126. A1 x to the 7. Of course we can go further. Now let's group all the x0 term. Factor out a0. We have 1 and 1/3. Factor out a0 and 1/45 x to the 6, because this can go continue going, and then the others a1 x 1/6 a1 factor out 1/126 a1 factor out x to 7, and keep going. Right. So that's what we have is a power series solution to differential equation. I know this is a long section already, but I just want to show you how we can do this recursion on the calculator. If your major is computer science, later on you might appreciate what we're doing here. Right, so what we have is a sequence of numbers, a sequence of coefficient, right? Where I cannot really type the coefficient a0 and a1. Calculator doesn't work like that. So I assume the simplest case is let a0 to be 1 and let a1 to be 1. So in this case, if we look at the calculator, the sequence now, the coefficient, a0 is a constant, a1 is a constant, a2 is 0. So we start the sequence as follows. 1, so we have a0, a1 is also 1, a2 is 0, and then a3, so we can continue. For a3 we can use that formula, and that's what we continue to enter in the calculator. Now, so that's what is the sequence. Now we're going to generate this sequence. Now the sequence of numbers is easy. The only problem is in the calculator we cannot type the sequence, the first term of the sequence. We cannot do that. The first term in the list of the calculator have to start 1. We cannot use the index 0. The calculator doesn't work. We say the first term of the sequence, or the first term in the list. We can also say like the first term in the list So in which case we write this as the first term in the list, first term in the second term in the list, and third term in the list. Right. And then the equation, let me just write out the equation. We have a sub k plus 2 equal to 2 a sub k minus 1 over k plus 2 k plus 1. Right, so we have that. Now we can put the solution out of the way. Now just focus on this. Now, notice that the index in the sequence and the index in actually what we have in the series are not the same. Then this is one more than that. So what we have to do, the first thing we have to do is replace this, increase the index by 1 to accommodate what we have in the sequence. So we have, instead of a sub k minus 1, it becomes a sub k. And change that to a sub k plus 3. We have to do that. Why do we have to do that? We do that because the sequence in the calculator, or we say the first term of the sequence, corresponding to a naught, so we have to do that to accommodate. The k here, we don't do anything with it, so we're going to keep it like that. And we write this, we will have a sub k plus 3 equal to 2 h of k over, let's multiply this out, k squared plus 3k plus 2. That is the relation. If we don't want k, we can use different letter. Right, now this is what we put in the calculator. We know the sequence starts with 1, 1, and 0. So let's start with 1, 1, comma 0, comma 0. And now we store, hit the STO key, store to a list 1. Now list 1, we start 1, 1, 0. What next is we'll generate the numbers. We're going to extend in the list. By the way, if you want things to be easier, use n or k, or you can use x. But if you want to use x, hit mode and go to sequence. So in that case, every time you hit that button, it's going to be n instead of x, if that's what you prefer. Right, now what we enter is going to be this. Of course, we cannot enter equal sign. What we actually have to be from the right hand side first. So we have 2 a1 of x. So we use n instead of k. And the L1 sub n will be the entry in the sequence. So 2 over n squared. Okay, we cannot do that yet. First, we have to say 1 store into n. So we start with n equal to 1. Yeah, I forgot to do that. And so we set initialization for the sequence and n equal to 1. Right, so we do that first. Now we do this recursion. 2 times L1 of n, right, divided by n squared plus 3n plus 2. When we do that, we're going to put in L of the index will be n plus 3. So when n equal to 1, 1 plus 3 is 4. So what it does is it's going to give us the fourth entry here. Of course, we can do that. Give us 1/3. Yep, 1/3, which is good. Now, but even better, because when we do this, we update the n, right? Increase the n by 1. So what I do is, instead of doing that, I will do that again. But this time I'm going to update the n, so n will be increased by 1. So to increase n, I hit alpha dot to the column here, meaning we do 2 calculation at one time. So we say n plus 1 store into n. So after it generate the list, update the n. So we do that, you will say n equal to 2, 3, 4, 5, and 6. How many do we have? Up to a of 7, meaning we need up to 8, right? Doesn't matter, we just keep going. And now let's look at the list. In fraction. Right, so 1 1, 0, 1/3, 1 6, 0, 1 over 45, 1 over 126, and then 0, the next one is 1 over 16, 20, and then of course if we want more, then we'll have more, right? So that's what we have, right? So of course, very important here is that in this case we assume that a0 is 1, a1 is 1, and this one very important. The only reason we can use the calculator is because this one is only depends on one term. If we have something like, it could be the case, a of k plus 2 equal to a of k minus 1 plus 2 a of k minus 2. If it depends on 2 terms like this, don't use the calculator, just have to work by hand. But this time it only depends on one term, one previous term, then yes, use the calculator. That help. Right, go to the previous example. Let's see if we can check this again. Right, on this one we have a0 a1 is a constant. So let's say a0, a1, 2, a3, and so on. a0 is a constant, so which is equal to 1, a2 0, a3 0, and after that there's the relation. And as before, the sequence that we cannot start at 0, we should have to start from 1, 2, 3, and 4. And what is the relation? Well, this is the relation. What we did earlier. Oh. Remember, because in the sequence we can use the subscript 0. I mean, in a0 we can write a0, but on the list in the calculator we have to start from 1. So before we do anything, this a of k minus 2 become a minus 1. So increase the index by 1. Right, now we write that a of k plus 3 equal to negative a of k minus 1. We only do that, the k plus 1, k plus 2 do not do anything. Right. Now, even then it's not done. We cannot put this in the calculator, because if we start the sequence with 1, with L1 of 1, if we put 1 in for k, that's going to be 0. I bet that means that start from 0, which is not in the sequence. So we have to do something else. Right. By the way, we can just keep that. Right, that's good. Now let's say the sequence now is what? 1, 1 for constant. 0, 0, right? store into, let's just store into list 2. So I don't want to mess with list 1, all right? And then the initial index. Now this is important. What is the initial values? Notice that if we're going to put 1 in for k, we have a of 0, which doesn't work in the calculator. The calculator have to start with the first one. It has to start with 1. So in this case we have to start from 2, because when we do that, 2 minus 1 is 1. So we actually have L2 of 1, which is what we have there. So do that first. Negative, okay, then n squared plus 3n plus 2, yep. Store into L2 of n plus 3, yes. Update n. Right, this should work now. That's enough. Right, now list 2. Right, change the fraction. Okay. Constant 1 1 0 0, negative 1 over 12, yes, negative 1 over 20, good, 0 0, 1 over 672, 1 over 440, and then 0 and 0, but just keep going with that. Right. Like I said, if we're going to use the calculator, we can try that, but the calculator, the sequence, the list start from 1, so we have to save the index, and then we have to know where we start, so that we don't put the numbers in the sequence have to be at least 1. So that's why we choose where we start on the calculator. Besides, in this case, if we're going to store an L of k plus 3, the first term we need is L1 of 5, so we need to have 5. Yeah, the first thing we need is L1 of 5. So in order to get 5, k has to be equal to 2. So that's why in this sequence, we start with n equal to 2. Because if we put 2 in here, we have the 5th term in the sequence. Do not use A, use L instead of use L, so that's less confusing. So it's L. Right. Of course, the calculator part is a little bit advanced, but I'm just going to show you how to do this by hand, which is should be able to do that. Anyway, with that, I stop section 8.3 here. As always, thank you for watching, and see you in another video in differential equations.